So welcome to lecture 18 of MCS 471, numerical analysis. So today we return or we continue our exploration of linear algebra, numerical linear algebra, and we also continue our last chapter on interpolation and approximation of data. So now we are going to look at problems that are over specified or over determined. We have more equations than unknowns if you look at linear systems. So we're going to define how we can solve such problems in the least square sense if we formulate this as an optimization problem. So in the first part, we will define the least square sense of solving a system. And then in the second part, we will start with the QR factorization. So we will see that solving it via the normal equations is actually not the right way to do it. It's okay if you do this on small examples with paper and pencil, but in this course, in numerical analysis, one uses the QR factorization. So in the second part of this lecture, we will define the QR factorization and also see how this relates to the least square solving. So much of what we have, what we are going to cover has already been covered in an introductory linear algebra course. So for some of you, this will be familiar. If not, this lecture is self-contained. So if you have not taken linear algebra, don't worry. This lecture is self-contained. So what is the problem? So we have some data points. So here you see the red dots, 9 of them. And we want to approximate the data with a line. So you see the blue line approximating the data. So if you would do this, if you would look at this from the technology from the last lecture, we would do a smoothing spline curve around these points. We would end up with something that looked very nice, a nice curve. But actually, what we here would like from the data would be the trend. What one can see from the line is that it's trending upwards. And the line sometimes fits the points. Sometimes the points lie very close on the line. Sometimes they lie very far on the line. So what we actually will try to do is we will try to minimize the distance of the points to the line. So that will be the objective. And you can see from the legend here, this experiment was artificially constructed. I started with a slope 0.5 and with an intercept equal to 1. So the blue line is the approximated line. So in a way, you could see this also as a data compression tool, where we want to replace the 9 data points, so the 18 numbers that represents the coordinates, by 2 numbers, by a slope and an intercept. So how was this plot made with Julia? It fits everything nice so in a way, this slide is also summarizing everything. If you have to do least square solving, then I'm here boxing it in. It is done with the backslash operator. So the backslash operator is very versatile. It will also solve in the least square sense once the problem has more equations than unknowns. One sees the plot. So I generated a range of points starting with x. Then the y are the points on the line with slope 0.5 and intercept 1. Then I added some noise to it, some noise of magnitude 0.1. and most 0.2 I go off the line. Then we have the setup of the linear system, so that will be defined in this lecture. And then we have the backslash operator. So in some sense, the essence of this slide here is that we recognize the backslash operator. If you're interested in plotting, then here are some very interesting plotting commands. So we are labeling so see the label is customized with a string where the coefficient of the computed coefficient is actually inserted into the label, and also the computed intercept. So C2 is the slope that comes out of this, C1 is the intercept. And then also it's kind of nice, there is this addition operator, component-wise operation. So there is the dot plus operator. So if the dot would not be there, we would be summing up the two vectors. And that's not what we want to do. So the points where we fit, so this is this fit y, so this is what we are going to plot. So that's actually the fitted line that gets evaluated here. So at our range of 11 points, starting from 0 to 1 in X, we evaluate the fitted line and then we plot it. And on top of that, we have the original data points, actually the 9 original data points. So the first point and the last point are omitted in these 11 points. All right, so this is towards applications, so where this is extremely useful. So now let's turn this into a linear algebra problem. So if we have 3 equations in 2 unknowns, so the unknowns are x1 and x2, then we separate the unknowns from the given coefficients by the matrix vector notation. So 3 equations and 2 unknowns. What we know from the very beginning from linear algebra is the matrix multiplication. So we have a 3 by 2 matrix. We can reduce this to a 2 by 2 matrix by multiplying the entire system, so both A and B, by the transpose. So here in this example, we have a 3 by 2. We multiply by a 2 by 3. And that leads to what we call the normal equations. So the problem is in some sense normalized. We have 2 equations in 2 unknowns by making a matrix product and a matrix vector product. So since we multiplied with the same matrix, both left-hand and right-hand side, we actually obtain the same system. Fine, what does this actually mean now? So let's look at this problem from the application perspective. How can this give us a least square fit? Well, let's look at the least square fit problem. So what is the least square fit? We have some data points. So here I want to do this within the same setup as we did last chapter. So we have x points and function values. All the points, the x's are mutually distinct from each other, and we want to approximate this with a line. So what these equations actually say, they are the interpolation equations. So here is the first equation. If you evaluate the line, so the line with intercept 0, a0, so we multiply 1 with a0, and slope a1, we multiply x0 with a1, then we must obtain f0. So this system here, I no longer wrote it in the full form, but you can see that this is the same as requiring the interpolation conditions. But of course, we can no longer do this with the interpolation conditions. Assume that we don't know the trick on the previous slide, and we want to do this all in earnest. So we're going to minimize the sum of the squares of the errors. So in full generality, we cannot have that the line passes through all 3 points. That will not happen for a generic data set. But what we can require is that we minimize the sum of the squares of the errors. So we have 2 unknowns, and the unknowns are the A0 and the A1, so the intercept and the slope, what we want to compute. And we want to define A0 and A1 so that our objective, so the objective is the sum of the squares of the errors. That's what we want to minimize. We see this objective as a function of A. So there are a lot of letters here on this slide, but the X0, the F0, the X1, the F1, the X2, and the F2, they're all given numbers. So this is one quadratic form that we want to minimize by taking the derivatives. Now, if you take the derivatives, so why this looks very cumbersome now, but taking the derivatives of a quadratic leads to linear equations. So actually, the reason why this method works is that we are going to end up with a linear system. Let's do it. So in full generality, we have our objective function, and we want to minimize solving this linear system of equations. So there are a lot of 2's there that come because of the derivation of the quadrics. So it's important that we can distinguish again between what is known and what is not known. It's not obvious when we collect the terms that actually the A0 and the A1 are the unknowns. So already here in collected form, you can see that the A0 and the A1 are kind of separated. So now we are ready to put it into matrix form. So the derived equations here are now written in matrix form, where we separate. Perhaps it's not entirely clear. Let me back up a little bit here. So I deliberately did not simplify here further. So the 2 plus 2 plus 2 remained 1 plus 1 plus 1 on this slide here. Why is that? Well, we want to untangle these equations, write them as a matrix product. Why is that? Well, you see that if we look at this problem a little bit more carefully, and especially the right-hand side is now very interesting to look at. So we have the sum of the function values, and then we have the function values again, but multiplied with the points. And we can write this in a matrix vector product. So in some sense, this is a fancy way of writing it. What does this buy us? Well, look at if you do the same thing at the right, at the left. So at the left, we can do the same thing. So at the left, what we do is we have the 1 plus 1 plus 1 that comes from the matrix that we found at the right. And we also have, there's still a typo here, we have here the x0 plus x1 plus x2. That's also what came out from the right. So the matrix that we obtained from the right now appears at the left. And we have yet another matrix. So that now this is another important matrix that appears. We have encountered this matrix before. And you see that they are very much related. So if you know one, you know the other. You just have to look a little bit differently. You have to take the transpose. So what is the conclusion of this slide here? Well, the main point is that solving the linear fit problem in the least square sense, where we want to minimize the errors, that actually corresponds to solving the normal equations. So we've done this here for a line, but this will be true in general. So that's where we then going to generalize this problem. When we have, in general, we may want to consider only the trend if we have some data points, but it could also be that we want to check whether our problem comes from a quadratic, whether it's a quadratic shape. Before we go in full generality, let us look at the numerical example. So this will be the running example through this lecture. So this lecture was still fitted, adjusted from a paper and pencil or from a blackboard lecture, chalk and blackboard. So where everything could be written down numerically as well. So let's do this. So we have 3 data points, 0, 1, 1,1, and 2,2, and we want to fit those data points using the normal equations. We set up the matrix form, we compute the transpose, and multiply this transpose both to the left and both to the right. So we have a 2-by-2 system that we then solve with one simple row reduction. This example looks very simple. Let me point out at one property here, which I didn't point out earlier. Notice that the matrix that you get looks kind of nice. So in the sense that it's symmetric. So the 3 that is lower diagonal also appears in the upper diagonal. It looks a coincidence, but that is a general property. Remember the lecture on positive definite matrices and the Koleski decomposition. Here I'm doing only one row reduction because I'm interested in the solution, but if you would be interested in the LU decomposition, then you would do a Koleski factorization. All right, let's look at the problem full generality. So we have a number of data points where all the x values, all the interpolation points, although we no longer call them actually interpolation points, we call them the x's or the abscisses of our data, the first coordinates, so they're all mutually distinct. So actually we want to fit a function, so that's important. So last time we looked into fitting, we approximated curves with the Bézier curves. It was important there that we understood the difference between a function and a curve. Here we're still working with functions. So for every data point, there is a unique function value. So we are fitting functions. Fitting them with a polynomial and fitting in the least square sense. So we're going to minimize this. We're going to find the d+1 coefficients in the least square sense by solving a linear system. So with interpolation, and this matrix actually is very familiar. I can write it down. It is again the van der Monde matrix. So in the interpolation problem, we also started out with a linear algebra problem. But then with linear algebra, so we actually then saw that with the interpolation algorithms, we could circumvent, we actually had better techniques than solving a linear system. So it was only when we returned to splines that we saw linear systems again. But here this will essentially be an entirely linear algebra problem. Now this is linear algebra, even if the van der Monde matrix is very structured. So it is an over-constrained system, n+1 equations and d+1 coefficients. So the number of data points, for every data point we have one equation, and the number of coefficients determines the degree -1, or the degree to which you approximate, you have d+1 coefficients. Here is a very first exercise. It looks very mechanic, but in a way, the purpose of this exercise is actually recognize the shape of the data. Does the data come from linear? Is there a linear pattern in the data? Is there a quadratic pattern, or is there a cubic pattern? So the midterm is coming up, and in one of the questions in the midterm, I drew shapes of points, and then you can look at the shapes of the points. So for the first data set that we looked at, in the very first set, we saw that there is a line, so there is a linear pattern upward trend. But it may also be that your points actually go down, follow kind of a parabolic shape. And you could also that they go up and then down again, which may suggest a cubic shape. So here, the purpose of the exercise is that you get familiar. So showing the steps in the method is that you set up the van der Monde matrices. So there are 3 of them, for degree 1, degree 2, degree 3. And then you use the backslash operator to solve, and then you compute the error, which fit is actually the best fit. So in a way, there is a sentence missing from this exercise. So I will write it here. So which degree fits best? So that is the point of this exercise. So towards applications, one wants to notice the shape of the data. So in general, one may have a point cloud, and what is the degree of the point cloud in a way? Notice that we have actually already seen with interpolation that there is a way to do this, but now actually we always use, we typically have more and more data, so the problems are over specified. And there may be outliers. So I should say that least square approximations are also very well studied within statistics. So there is also an entire statistical interpretation to the least square problem. So let us formalize what we have experimented with now. So we have the normal equations, so full in generality, so A transpose, we multiply, and then we obtain a square system. So in general, M is larger than N. We have seen that we derive then the solution of the least square sense. So we minimize the residual, the square of the residual. So we will also have a residual. So, and in a way, going back to the previous exercise, you should actually compute the norm of B minus AX. So that's what we did also when we solved linear systems, that's what we do still. Now, when we solved fully determined linear systems, it was kind of nice when everything worked out, we found a number close to machine precision. And here it's not going to be so nice, because sometimes if you compute this number, you may find quite a large number, and that makes us uneasy. Now, the geometric interpretation is important. So one very important property is that the residual vector is perpendicular to the column space. So it's actually perpendicular to the space. So it's interpreted that the right-hand side vector is actually projected onto the column space. Okay, so here is this. So we derived the least squares problem via partial derivatives, the way you would do this in calculus. But we can also see this differently, more with linear algebra. So the sum of squares is actually an inner product. And then we exploit the fact that we have the normal equations. So we can replace x. So we actually formulate the least square systems. And what we actually find is that the residual vector is perpendicular to the linear combination of the columns. And actually there is more. So you can actually also say that solving in the least square sense means that the residual vector is perpendicular to all the vectors spanned by columns of the matrix. So here you can see AX, the geometric interpretation essentially of doing A times AX is to making a linear combination of the columns of A. So you see these vectors here. Look at the second index. The second index is the same for all these vectors. So we are making a linear combination of the columns. Now, if this is true in general, this is implied by the residual vector being perpendicular to each column separately. And how could you prove this? So this is a stronger result, essentially, than what is explained here. You could take X to be the first unit vector. So you take any matrix, and you will see that if you take the first unit vector, then actually you will be perpendicular to the first column. So there is this linearity of the basis that matters. Now, one picture says more than 1,000 words. So in a way, this is the most important picture. There is a Jupyter notebook associated with this, where for this running example, solving this example is completely trivial. But what is interesting to look at is the residual vector. So the residual vector is drawn in red. So this is the red line segment. So you take the solution, you multiply the solution with the matrix A. First column is 1, 1. The second column 1, 1, 1. The second column consists then of 0, 1, and 1. And the residual vector is then the right-hand side vector, which is 1, 1, 2, the y-coordinates, minus these A times X. So the columns of A are drawn in green, and you can see, and the main point here is that you have this orthogonality. So the two green line segments, so actually they are vectors. So the two vectors span a plane geometrically, and the residual vector will be perpendicular. What does this mean? Well, this means that this perpendicular thing can still be checked. So if I call the residual vector R, then R transpose A will actually be 0 or close to the machine precision. So this is the important property. We can still have a residual in the very convenient usual sense, where we still expect a number very close to the machine precision when everything goes well. So in a way, this summarizes the least square part of solving. So in a way, mathematically, the normal equations are actually a very satisfactory, give us a very satisfactory answer to our problem of solving overdetermined linear systems. Of course, this is a course in numerical analysis, and the lecture is not over yet. So let me continue. We are worried about the conditioning of this problem. So this problem will be very bad conditioned when some of the points are the same. But actually what I want to explain here is that the normal equations are actually making the problem worse. Let's look at the condition of the system of normal equations. So remember, the condition number is magnifying the errors on the coefficient matrix. Formally, we define this as the norm of the inverse times the norm of the matrix. Now let's look at condition number of A transpose A. We are still assuming that the problem is well posed. So the general problem of fitting many points with a lower degree equation will still be badly conditioned when some of the points are the same. But you can now already see why one would take many more points. So it suffices that you have sufficiently many points that are distinct from each other. So in a way, fitting with many more points than you really need makes your fitting more robust. So that's also a way of seeing how the problem is actually a better problem than the interpolation problem. It may happen that some points are actually the same, but the fit, that's not going to matter that much. All right, so let me go through the point of this slide. So we are trying to compute this can only happen when the matrix is square. Typically condition numbers are computed with a singular value decomposition. And we will get into the singular value decomposition at some point. So here we do some manipulation. So the inverse will invert. So the inverse of a product is the product of inverses where you flip. So this is a property that we haven't recalled, but we're using this here. So you may have covered this in linear algebra. The inverse of A times B is the inverse of B times the inverse of A. So we use this in the first step. Then we use the norm inequalities and we regroup. And this is actually the whole point, is that in the worst case, the condition number of the A transpose A can be the square of the original problem. So that means that if your condition number is 10 to the power 6, then the normal equations may have condition number 10 to the power 12. And that's significantly worse. So the next exercise invites you to experiment with how bad it can be. So for this exercise, we must go back to lecture 9, where we constructed matrices with a prescribed condition number. How does this go again? Well, you construct a random actually, you start with the diagonal matrix, the identity matrix, and you turn the last element to 10 to the power minus 6. So the best matrix is the identity matrix. So you start with that matrix, and the last element turn it into 10 to the power minus 6. And then you multiply A with a random orthogonal matrix. And we will see that this can happen. We did this already, but this is with the QR factorization. So you generate a random orthogonal matrix, and you pre-multiply and you post-multiply. And then you apply the COND command twice, once on the original matrix and once on the matrix that you come from the A transpose A. Now, it may be that you see 10 to the power, it may be that's actually the worst case, but you should actually see something worse. So repeat this experiment for increasing dimensions. So it could be that dimension 10 was still a lucky dimension, but if you do this a couple of times more, you will actually see that the condition actually gets worse. So doing the normal equations is fine in paper and pencil for small examples, but it's not so fine for larger problems. All right, so let's then come to the second part. We will now see how a QR factorization can be used to solve a least square in the least square sense by also reducing this to an upper triangular system. And we will see again how this happens in Julia. So in a way, this lecture is almost over. So the most important topics have already been covered, but there is still something more to be said. So what is DQR factorization? So the first word is already important. So if you have a given matrix, then there is also a unique factorization. So we can speak of the QR factorization. So in a way, the definition also implies that there is somehow some theoretical justification of this. So in a way, it's also like the LU factorization, although one should keep in mind the pivoting. So what we have, it's a factorization, and it reduces the matrix to a product of an orthogonal matrix. So that orthogonal matrix will have to do something with the way that the matrix is reduced, and the matrix is reduced to R to an upper triangular form. So you can see the QR as a rewriting process, and we will do some of that rewriting. We rewrite this, but then there is an entire geometrical interpretation for it. So here it's kind of important that we have the dimensions right. In a way, I use here the orthogonality for Q to be M by N. But as we see with Julia, this will be M by M. And that will hopefully become clear in the next lecture. Julia uses not the modified Gram-Schmidt, but the householder QR factorization. So the N is fine if we think about the householder QR, the modified Gram-Schmidt, the more geometric interpretation that we have an orthogonal basis for the columns of A. If we see this as a transformation matrix, then the Q is an M by M matrix. So this might be a confusing definition already now. Now, from a strictly utilitarian point of view, so from a practical perspective, how do you use the QR factorization? Well, if you have a QR factorization, and the point of orthogonal matrices is that they are the nicest matrices to take the inverse of. So you just have to see the rows as the columns and the columns as the rows. So, but you also do the multiplication of a transpose, but now the transpose is a very nice matrix. So the very nice matrix here will not lead to a Wurzer conditioning. So again, if you do the exercise 2 with an orthogonal matrix, then you will see that the condition doesn't deteriorate. So in a way, here by this reduction, so by the Q transpose times B, which is very reminiscent of the normal equations, we do not magnify any errors. And we have obtained an upper triangular system. And these upper triangular systems are also well conditioned. So what we remember from the second project, due soon. This slide summarizes everything one needs to know. This is an experiment. I fitted everything in 2 columns, but you should read the first column first. So read the slide. We are using the linear algebra module because we use the QR command on a random 3×2 matrix. And we verify 2 things. We verify that the matrix Q is indeed transpose. Q transpose Q is the identity matrix. So the matrix Q is indeed orthogonal. We have the factorization. So here, first column, second column. Of course, I'm displaying this only with 5 decimal places, the default. But you see that all the numbers actually match. And then you see that the R is also upper triangular. What I actually, a verification that we actually still should be doing is that the transpose, so actually the transpose Q times A should be R as well. That is actually implied by the transpose Q times Q and the Q times R. So you can see the matrix Q, if you transpose it, also as a way to triangulate the matrix. It's very similar to the L in the LU factorization, where we had the multipliers. The L is a lower triangular matrix that is used in the solving, but it also stores the multipliers. The Q is also going to store the information needed to make this matrix upper triangular. All right. How would you compute the QR factorization by hand? And this is something that you may have done in a linear algebra course before. Or if you haven't done it, then this next slide are kind of doing the course, but then in a more elementary fashion. So if you did not have a linear algebra course before, then going through this example may be very useful. So we are seeing this problem now as a more geometrical problem. We are going to compute an orthogonal basis for the span of the column space of the given matrix. So we see the matrix now not as a matrix, but as a sequence of vectors. Q1 will be the new first column. And why is that a good choice? Well, if you make the inner product of Q1 with Q1, you have the unit vector. So remember the orthogonal basis, all the vectors need to be orthogonal. And then we are going to make the second vector by projecting, by subtracting from the second vector the projection in the direction. So here we go through this in a pure algebraic way. There is a geometric interpretation of this via pictures, which I hope to explain in the next lecture. The normalization is important. For me to make a good picture, the picture to show that the residual vector is orthogonal to the column space, also for the same running example here again, then I needed to do a normalization of the vectors. So here we compute Q1 and Q2. You can verify that because of this subtract from A its projection in the direction of Q1, that if you make the inner product of Q1 with Q2, that you get 0. So we have orthonormal vectors, so we have done the normalization, and we also have an orthogonal basis. So the point of this example is actually to illustrate another important property of the QR factorization. So if we have a QR factorization, we not only have an upper triangular matrix, but we also have an orthogonal basis for the column space of the matrix A. So we have something extra. So we have worked backwards. What we computed, say, let's compute an orthogonal basis. We actually have obtained the QR factorization. Now, reasoning backwards, when we do the QR factorization, we actually also compute an orthogonal basis. So that will be the basis for the modified Gram-Schmidt method. And actually, we have already done now 2 steps in the modified Gram-Schmidt method. The purpose of here is to use Julia. We did everything with the exact numbers, but actually in a computational course, you would use the Jupyter notebook and illustrate everything step by step. Here is then the running example again. So instead of giving the matrix, we now give the 3 points. We set up the van der Monde matrix and we compute not anymore the normal equations, but we compute the QR factorization. The QR factorization that we have done already. So there is then a product to be done with the orthogonal transpose of the Q to get the 2 by 2 linear system. That's then is solved. And we have the same solution as with the normal equations. All right, some important properties of the QR factorization. So the QR factorization solves the problem in the least square sense. That's the most important sentence that summarizes this entire lecture. For numerical stability, the lemma is extremely important. So we are going to transform matrices, and orthogonal matrices are length preserving. So this is what this lemma says. And this lemma is used here in the proof, but we will use this lemma in transformations, in orthogonal transformations, to compute a QR transformation. So here we use the proven dilemma, so that if we are going to the equivalent system, we are multiplying with an orthogonal matrix. But an orthogonal matrix does not change the length. So if you go from the AX equals B system to the RX equals Q times B system, you don't change any norms. So you don't change the residual. So that's actually the conclusion of this lecture. There is one more application. So we can also do this for tree space. So this is a modeling question where you have to figure out how to set up the coefficient matrix. So you do this, you can do this. This is a paper and pencil exercise. So the first part is a paper and pencil exercise where you can write down first all the equations, and then you group the equations in a matrix form. Now we have a multi-dimensional data set, and we want to fit with a plane. And then let's do this in Julia. So I will stop the recording.